Good morning, dear students. With the few past paper questions done in the last lecture for practice, and with the comprehensive discussion of those past paper questions, we are now in a position to move on to the next topic, that is capacitance. And you will see that we'll revisit many concepts that we have just learned in the topic electric fields. So this chapter is a natural continuation of the last topic. You will also notice that in the past paper questions, this topic is often combined with electric fields. So electric field and capacitance is often considered a single topic because the two are very, very similar concepts. Various things overlap. So often a question in the exam that appears is from the two topics combined. The name of the topic, capacitance. We can start with the definition of capacitance, but before you understand what capacitance is, we need to understand what is a capacitor, its construction, its working, and only then you will appreciate the idea of capacitance. A capacitor is typically two conducting plates separated by a small distance and then connected to some difference of potential on the two ends, which simply means that we connect it to the two terminals of a battery in this manner, like this. We have a switch here. I am ignoring any resistance connected for the sake of simplicity. When I close this switch, there is some current noticed in the ammeter. Although there is a gap, there is no connection between these two plates, but there is some current that flows in the circuit. So this is a bit of surprise because in the open circuit, there is no current possible. So with this switch closed, although the circuit is still open, some current flows. The reason is that the charge that flows, and it is same conventional current that can be assumed to be flowing from positive to this side. So positive charges may be imagined to be flowing from this direction and they accumulate on this plate. Naturally, this doesn't happen at once. It is one charge that comes first, then the second charge that comes, then third one. And as we have more charge accumulated on this plate, the further flow of charge gets repelled because more positive charges coming to this side will become difficult now because the charges present on this plate that are not moving any further. They are getting accumulated here and they will repel the charges coming further. So the rate of flow of positive charges will drop gradually. But one thing that will side by side take place is that these positive charges will attract equal and opposite negative charges from this side. So this will result in accumulation of equal amount of negative charge on this plate. So induction is the idea which is at work here. So what is happening here is when you close the switch, current starts flowing, the conventional current with positive charges flowing like this and getting accumulated here, inducing equal and opposite charges on the plate immediately next to it with a very, very small gap in between. Sometimes there is no material placed inside. Sometimes we placed an insulator in between to improve its working. I'll explain later how the insulator, which is known as dielectric material, how by placing a dielectric material, an insulator basically, that improves the working of this capacitor. We'll discuss it in detail later. But for simplicity, we assume that there is nothing in between, it's a gap. So there is no touching here. It is equal charge that's induced on the other side, which means negative charges are attracted. So they flow from this side of the battery and move on to this plate. So while we are accumulating a positive Q charge on here, positive Q charge on this plate, negative Q charge is accumulate on the other plate. So if I ask you what is the total charge accumulated on the capacitor, the answer is 0, because equal and opposite charges cancel. So the net charge stored on a capacitor is 0. So our definition of capacitor is challenged here, that we have been learning in the previous classes. What is a capacitor? We used to define it like it's a device that is used for storing charge. But if asked a question, what is a charge stored on a capacitor like this, the answer is 0. So that means this is not an appropriate way of defining. Instead, we say that electric capacitor is a device that stores electrical energy. So although charge is 0, but battery has done some work, and as a result, there is a field created, and that means some electrical energy is now available in the form of this electric field. If you place anything in between these two plates, it will move to this side or to this side if it has charge. So therefore, electrical energy is stored by separating the charges and in creating that electric field, in creating the difference of that potential. So this is the electrical energy that is stored. So the first thing that is important to you to know and to understand and remember is, what is a capacitor? What is a capacitor? And you will not say it is a device that stores energy, that stores charge. And they have asked a question like this: why is it inappropriate to state like that? They have asked this question in one of the past paper questions as well. Why is it inappropriate to say that capacitor is a device that stores charge? And we have explained the reason, because the total charge in this type of capacitor is 0. So instead of stating that capacitor is a device that stores charge, we state that it is a device or an electric component which is used for storing electrical energy by doing work in separating charges on the plates. So charges are accumulated on the plates, and although the net charge is 0, but since the battery has done work in separating them, accumulating positive charges on this side and inducing or attracting the opposite charges of the same amount on that plate, and as a result creating a difference of potential, an electric field, so that the electrical energy becomes available and we can make use of it whenever we want. So this is the energy which is stored on a capacitor. It could be enormous amount of energies that capacitors use and they store, and this depends mainly on the size of the capacitor, the size of these plates, and in many cases, especially in those situations in which a huge amount of energy is required. Suddenly, we have a very large capacitor, sometime of the size of this room. So we have two huge plates side by side with an appropriate material inserted in between, sandwiched in these two plates, and we accumulate charges. And suddenly when we connect these two sides to any device to which we want to deliver that energy, this is the energy, the kind of difference of potential due to which a huge amount of energy is transferred to that device. So this could be a flash in the camera, which is using this device, or other situations in which you want to create a spark, a large amount of energy suddenly delivered to a situation. So capacitors are usually used in those situations. Now we are in a position to understand what capacitance means. So I go back to the word capacitance now. What do we mean by capacitance? Capacitance is basically the ability of a capacitor to accumulate a charge Q with the help of a given potential V. Suppose the difference of potential that you have provided to these two plates is V, and as a result you have accumulated Q charge on each plate. This is positive Q on this side, negative Q on this side, but it is Q on each plate. The magnitude is Q. So capacitance is capacitance is the charge on each plate of a parallel plate capacitor, per unit potential difference, or per unit voltage applied across the capacitor or the two plates. So as the figure is suggesting, you have applied a difference of potential to these two plates, and as a result you have accumulated Q charge on each. If this Q is large for small value of this V, obviously you have a large capacitance of it. And even if you provide a large value of difference of potential, but the charge is not that much, the capacitance is obviously small. So mathematically speaking, the formula that gives us capacitance, mathematically it is charge stored per unit potential difference applied to the two plates. So simple definition. So this unit is therefore, it is always capital C that is used as the symbol of capacitance. So you will remember capital C as capacitance. The unit is obviously, unit is clearly coulomb per volt. This is a scalar quantity because this is charge stored per unit potential difference. Coulomb per volt is the unit of it. But there is a special name for this unit, and that is farad. F-A-R-A-D. Farad. So they often ask you, what is farad? The farad. So farad is defined as it is 1 farad capacitance, or the capacitance is said to be 1 farad, the capacitance is 1 farad. If I wrote only farad as symbol, then it is capital F, but full name for the unit is with small f. I hope you understand the reason of this. The capacitance is 1 farad if we can store 1 coulomb charge by providing a potential difference of 1 volt. By providing potential difference of 1 volt. So this equation clearly tells us the relationship. This is 1 coulomb exactly. This is 1 volt potential difference. And this is exactly 1 farad of capacitance. This one. But farad is a very large unit. You will probably never see a capacitor with such a capacitance. Most of the time, the capacitors that we come across in various devices, they are used, in fans they are used, in all the UPS and all the computers, capacitors are often used, but they have very, very small capacitance, often picofarad, microfarad. Most of the time, micro and picofarad are used because 1 farad is large, because 1 coulomb is a huge amount of charge with just 1 volt potential difference. This is possible only if we have a very large capacitor using, and that of course rare. In only specialized situations we create very large sized capacitors. Often they are very small in size, and therefore their capacitance is in the range of micro farad, nanofarad, picofarad. So this is capacitance. Now, as I said in the beginning, as we close the switch, the charge starts accumulating on it. There is some current that we detect in the circuit. Now, there are questions in the exam that want you to understand, expect you to interpret those graphs, how this current should vary with time. This is IT graph. You detect a current here as soon as you close the switch. Initially, this is an uncharged capacitor. There is nothing on each plate. But as soon as you close the switch, you detect a current here because the charge starts flowing and starts spreading itself on this plate uniformly, because this is a conducting surface. Usually a copper is used on the as two conducting plates. Sometimes those other conducting materials are also possible. What is the variation, the manner in which the current varies? As soon as you close the switch, current is large because there is no repulsion to the charges. There are no charges already on the plate. So what is expected? We have a large current in the beginning. As soon as you close the switch, there is a large current detected. But with time, that current decreases in this manner. So this is the kind of graph that you will see in various past paper questions. That current drops in this manner, kind of exponential drop, a gradual decrease, although there is no equation in your syllabus that require you to do to make use of the exponential function here, the way we used in the case of ultrasound in which attenuation took place, and we did calculate how the intensity decreases exponentially, and there was a function that we are calling exponential function. Here we don't have to worry about any such calculations. There will be simpler calculations involved here. What is the current at this instant? What is the current in the beginning? And after this, how much energy will be lost? So we will learn those formulas which require those calculations. So this is a simpler graph, simply showing that current initially is large, it gradually decreases with time, and then after a long time, there is no more current in it. But what happens to the charge here? Initially, there is no charge here. I'm talking about just one plate. So initially on this plate, there is no charge. Then because current is large in the beginning, so rate of accumulating charge on it must be large. Rate of flow of charge must be large. But as the current drops here, the rate of accumulating charge here must be smaller. So what is the shape of the graph that we expect if we want to plot a graph between Q and T with time? Charge is accumulated on the plate in this manner. Look at this. So again, in the past paper questions, you have this type of graph in which charge is plotted against time for each plate. This simply means that with the time, more and more charge is stored in the beginning, but this rate of accumulating charge on it, which is Q over T, which is gradient basically. So Q over T is gradient always. If it's a straight line, that means Q over T is constant. That means current is constant in it, but practically this is not constant current. Initially it's large value, as I have shown you like this. If in some situations they give you a straight line for Q over T, that of course means that current has remained constant in it, maybe in a controlled manner, that is possible. But if we have no resistance at work here, or very small resistance involved, and we allow as much current as it flows in the beginning, and then it naturally decreases as more and more charge is accumulated here. This is the manner in which charge, initially it's a large rate of flow of charge, but that rate of flow decreases, and then the rate of flow of charge becomes zero because the charge is now constant. So it is the charge Q that is accumulated finally, and then even if you keep this switch closed for another, let's say few minutes, charge will not increase on it. So this is the maximum charge a capacitor can store, and that is what its capacitance is about. Now, the last thing is how do we know that after a certain amount of charge stored on it, or after a certain amount of current flowing in this circuit, we have a certain amount of energy stored on the capacitor? In order to understand the energy stored on a capacitor, energy stored on a capacitor, we have a simple formula to derive, and that is based on the same concept that you learn in your AS classes. Energy stored when you have a uniform electric field established due to a charge here and a charge here. That means the energy that you have stored on this capacitor is V, the difference of potential, multiplied by the charge. This is actually the energy involved here. If I have moved a charge Q, the total charge that I have moved to this plate, and as a result, that is the induced charge by the same amount on that plate, but we are talking about just one plate at a time. So if I have moved the total of Q charge to this plate with the help of this difference of potential, that means the total work which is involved here must be this. But there is a problem in this equation, that is, I have not sent this charge Q in one go. I started with 0 and then slowly it is the final value of Q that I have accumulated on it. So instead of writing Q here, we average it for two values. We write it like this. So for a capacitor, the total energy involved is 1/2 QV, because the charge that I have accumulated is also, although capital Q, but I have not sent that charge in one go. I'm repeating, I started with 0, so we have initial value of charge 0, and finally its value is Q. So this is an average that must take to make this the average kind of work that we have done on it. So this is the energy, the work that we have to expend in order to accumulate charge Q with the difference of potential. And this is the expression that we used to calculate the energy stored on a capacitor. Now it's easy for you to understand. If I have, let's say, 9-volt battery, and the capacitance is 9 picofarad, what is the energy that this capacitor can store if it is fully charged? So for a capacitor fully charged with this capacitance 9 picofarad, and I use 9 volt of battery. So you make a slight change in the expression. Instead of this Q, you go back to original equation where we wrote Q is equal to CV, this equation. C is equal to Q over V. So this Q can be expressed in terms of capacitance and voltage, and then this same expression will look like 1/2, and Q is equal to CV, so CV square. A more useful formula is this, CV square, because often the capacitance of a capacitor is given and the voltage difference that we have applied in order to charge that capacitor is also given. If I know these values, I readily put these values in this formula. C is 9 picofarad here, and 9 is squared because volt is the SI unit already, no need to change, but this is 9 into 10 to the power minus 12 pico. So with that, you can calculate how much energy we have stored on that capacitor, and that is the work that this battery has to do in order to store a given amount of charge. Of course, we can calculate how much charge it will store. So Q is equal to CV readily gives me the charge stored on it. And instead of this equation, I can also use this, because if I know the charge stored and I know the V, I can use the same equation. But in order to use this equation, I will have to calculate the amount of charge stored first, which is from this equation, Q is equal to CV. So simple formulas are used to do these calculations. So I stop here for today. We'll discuss a few questions related to this tomorrow, and then I'll share a few questions as a worksheet. Thank you for today.